In this video, I'm going to talk about or probability. So before we jump into the probability, let's just discuss the meaning of the word or. There is what's called the inclusive or and the exclusive or. Inclusive or means that you're given the option of two things and they both could possibly be true. Both events can happen. So let me give an example. Let's say you're at Thanksgiving and the host tells you you can have turkey or ham, assuming, of course, you eat meat. The implication here is not that you can only have turkey or only have ham. Really, it isn't. It's the idea that you could technically have both. And it's that fact that helps you kind of distinguish between the inclusive versus exclusive. Both would be allowed. It would be very rare your host would say that if you put turkey on your plate, you can't have ham later or at the same time. Okay. In fact, it's the or both that you could add at the end that makes it understandable that this is inclusive. Both of these things can happen. You can have turkey, or you can have ham, or you can have both. All right. Exclusive or is when only one event can happen. Okay, so here, an example of this would be you show up to class on time or you are late. That's an exclusive or, okay? The idea is it has to be one or the other in this circumstance. You either do show up on time or you're going to be late. All right. In this case, they can't both happen. You can't both be on time and late. That doesn't work. Okay. So that's the idea between exclusive and inclusive or. Okay, so let's go ahead and look at some examples, and we will kind of touch on this as we are going through some examples of the OR probabilities. So let's go ahead and look at this one. Let's using a standard deck of cards, okay? So from a standard deck of cards. Oops, that did not look like a C. Standard deck of cards. What is the probability? You choose a 3 or a queen. Okay. So in this case, this would be an exclusive or because you can't have a card that is both a 3 and a queen. Okay. So let's start by finding the probability that the card is a 3. Okay. So if you haven't looked at the deck of cards or don't remember it, go ahead and reference that. And I did talk about in the and probability video. But there are 4 threes in the deck out of 52 total. So that's the probability that you're going to get a 3. Okay. And then the probability that you'll get a queen is actually the same. There's 4 queens in the deck out of 52. And since both of these are possible, they kind of stand alone since they're exclusive. So what we'll do is we'll add those probabilities together. And that'll give us, let's see, 8 over 52. And let's see, I think that's reduces to 2/13. And I don't remember the decimal, so that's okay. I'll just leave it as a fraction. Okay, so this is the formula or the basic formula for finding probabilities, okay? So before I do that, I wanna define what we just saw here, these exclusive events here. Here's how we define them in in probability. Okay, so here's my definition. Two events are mutually exclusive. Another phrase that's used for that is disjoint or disjoint. So two events are mutually exclusive or disjoint if they cannot both happen. All right, meaning it has to be one or the other. They're exclusive. And it makes sense when we are actually literally throwing in the word mutually exclusive. Okay, it's an exclusive or. All right, so here's how you find the probability when you're working with mutually exclusive events. You just take them and add their probabilities together. Nice. Pretty straightforward. Okay. So here, I'm going to look at another example. Let's say this time, let's say we have a spinner. And I'm just going to roughly draw one. And let's divide it into 8 pieces here. So cutting everything in half. Okay. And then here, let me label them. Let's say that this is, oh, sorry, let me start up here. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8. And then we'll go ahead and say that half of the spinner has the color yellow. So these all are yellow, and the other half will be white. Okay, so let's find the probability that you spin a white number or a number less than 3. Okay, so a white number and a number less than 3 are mutually exclusive. So really quick, a number less than 3 would be 1 or 2. Okay, those two qualify because both of those numbers are less than 3. All right, so 1 and 2 happen to be on the yellow side. Therefore, they're not going to be white. So this would be exclusive. So let's go ahead and find the probability then of getting a white or less than 3. Okay, so probability of white is going to be, there's 4 wedges out of 8 total. Probability of being less than 3 would be 2 out of 8 because only 1 and 2 qualify. And that'll give us 6 out of 8 or 3/4, which I happen to know the decimal on that one, 0.75, if you want to write it in decimal form. Okay, one more like this, and then I'm going to show you the inclusive or. Let's say we have cards. I'm just going to draw them roughly here. So let's see, 6 cards total. Pretending those are all perfect rectangles. Okay, so we have an X on this card, a Y on the next 2, and Z on the last 3 cards. Okay, so what is the probability of drawing an X or a Z? And this would be mutually exclusive because the cards are either going to have an X, a Y, or a Z on it. So you can't have both an X and a Z. So let's find the probability of drawing an X and then the probability of drawing a Z. So for X, there's a 1 out of 6 chance that can happen. For Z, that would be 3 out of 6, which gives us 4 out of 6, or 2/3. Or if you want the decimal, 0.67. Awesome. Okay, so there we go. There's all our examples for mutually exclusive. Okay, now let's say this time I'm interested in kind of changing it up. Okay, I'm interested in looking at an inclusive one. All right, so I'm going to start by doing a different type of example, and then I'll give the formula. So I'm going to make a little table here of information. Okay, and so the first thing is we're talking about red cars, and then not red car. I'm going to give some space also because I'm going to put totals in here as well. Okay, so we have red cars, we have not red cars. And then you're going to get, one is that you get a speeding ticket or you don't get a ticket. Here, actually, maybe I should say ticket instead of speeding ticket, or speeding, I mean, since I'm trying to abbreviate here. Okay. And then the last column here is going to be the totals. And then the last row is going to be the totals. Okay. So we've got 15, 45, 60. And we have 135, 470, and that totals up to 605. And then this first row actually totals up to 150. Second row totals up to 515. And then those, both the row and column, total up to 665. Okay, cool. So there's our basic information. So you're in a red car or you're not in a red car. You get a ticket or you don't get a ticket. And this is speeding ticket. All right, great. Let's ask the question. What is the probability of a red car or a speeding ticket? Okay, so that's very poorly worded, and I should have worded it a little bit cleaner. What I really wanted to say is if we're talking about people, and the information that we've gathered from people is we asked them if they drove a red car or not, and then whether they got a speeding ticket or not. Okay, so what is the probability of selecting someone who has a red car or got a speeding ticket? That's how I should have said that. Maybe I should clean it up. Probability of selecting someone who drives a red car or got a speeding ticket. Sorry, being a little bit lazy with the way I worded that. Okay, so now this question is our first question that is not exclusive, meaning it's possible that somebody can drive a red car and possibly have gotten a speeding ticket. How do I know that? Because right here, there are 15 people who drive a red car and got a speeding ticket who literally exist in both of those groups. Okay. So in that case, then we have to take into account that there are 15 people who can do both. All right, so here's what we do. We kind of approach it the same basic way. We start by saying, okay, well, what's the probability that somebody is driving a red car? Okay, so the probability that somebody drives a red car, well, that is technically, I'd be looking at this first row. All of these people are people who drove a red car, right? So there's 150 people who drove a red car out of 665 people total. Sorry, I'm going to have to squeeze the screen a little, squeeze it all in. There we go. Okay. Now, probability of getting a ticket. Okay. So all the people who got a ticket, that's these people right here, right? All of those people got a ticket. So there's 60 total out of 665. Okay, but here's the problem. The 15 got counted twice. The people here, that 150 counts the 15, and so does the 60. So that group got double dipped. Okay, so we need to subtract that group of people out because they got counted twice. And what that looks like in the formula is we're looking at the probability that somebody is both red and got a ticket. Sorry, that they have a red car and they got a ticket. So that is how we would find this probability. So let's see, 150 plus 60 is 210, minus 15 is 195 out of 665. And here, let me go ahead and reduce that on my calculator. Oh, crud. 195 out of 665. There we go. Got to actually put it in correctly. Okay, that gave me 39 out of 133. Or if I wanted to divide that, that's 0.293. If I want to write it as a decimal. Okay, so this is our basic formula we're going to use when they're not mutually exclusive. Okay, so let's write the formula down. If A and B are not mutually exclusive, that's supposed to be a U, sorry. Mutually exclusive, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So what happens in this case is there's this double dipping like there was in the example above. It's the idea that this group gets counted twice because it's possible they could be in both events, that both events have happened to that individual. Okay. I wrote part A for that example, but I think I'm going to go ahead and abandon it and kind of come back to some of the examples I talked about earlier. So like from a standard deck, what is the probability so this time, probability of drawing, oops, a 3 or a diamond. So that kind of changes it, right? Because now we're saying, all right, it's possible for a card to be both a 3 and a diamond. They're inclusive. It's possible that they could be both. But I'm going to still find the probability of drawing a 3. Then I'm going to find the probability of drawing a diamond. And then I'm going to find the probability that a card happens to possibly be both. So 3 and diamond. Okay, probability of a 3. That's still 4 out of 52. Okay, but probability of a diamond, that's the whole suit. So there's 13 out of 52. Minus, okay, and then there is one card that is both a 3 and a diamond. So minus 1 out of 52. All right, so that gives me 16 out of 52, which reduces to, probably should know this, but oh well, 4/13, or as a decimal, 0.308. If I want to write it as a decimal. All right, so there we go. That's the probability with the fact that there's an inclusive or. I could do another example with the spinner. Let's just do that really quick. And I'll loosely draw the spinner again. So we had cut in half, 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 2, 3, 4, 5, 6, 7, 8. This time, if I want to do an inclusive, it's possible that's going to be both. Okay, so let's see. Let's do the probability of landing white or even. Okay, so in that case, the probability that we get a white one plus the probability that we get an even number minus the probability that it could be both. Shoot, I did not leave myself enough space here. Let me try that again. Probability of white. Even. Something is white and even. I'm squeezing it in. So I'm using the and symbol, ampersand. Okay, so that's supposed to be and, white and even. Okay, cool. Probability of white. Okay, so that's still 4 out of 8. The little number comes out white, or the wedge is white. Even would be, let's see, 4 out of 8 again, right? 2, 4, 6, 8. Yep. There's 4 numbers that qualify out of 8. But now there are numbers that are both even and white. And that happens to be the 6 and the 8 qualify for that. They're both white and even. Therefore, there's 2 out of 8. So let's see. 8 minus 2 is 6 out of 8, or 3/4, which is 0.75 if you want to write that as a decimal. And there we go. There is or probabilities.